Hi and welcome to this tutorial on the principles of covalent structures. So in the previous tutorial I introduced covalent bonding and we had a look at examples of single, double, triple and about their relative bond enthalpy or energies as well. So in this tutorial we're having a look at simple molecular structures versus giant molecular structures or giant covalent structures. So we know that the covalent compounds form from the bonding of two or more or between non-metals. So we're looking at that area of the periodic table. So depending on the extent of the covalent bonding in a compound, we can get two different structures. So we can get simple molecular and we can get giant covalent. You might see that referred to as macromolecular as well, macro giant. And if we have a look at my images here, I've got a simple, like three different examples of simple molecules. And actually we've got all the different bonding types, single, double and triple. But you can see they are separate entities. Okay, so a group of relatively few atoms joined together by strong covalent bonds. So two nitrogen atoms are triple bonded, covalent bonded together. And that nitrogen atom is not, they're not covalently bonded any further beyond that. There is this triple bond and that is it. There's no more covalent bonds being formed. Iodine, single covalent bond, there's no more covalent bonds being formed around it. And the same with carbon dioxide. This is a single entity. Okay, so it's just a molecule. But the individual molecules can be held together by intermolecular forces. So intra are these covalent bonds within, but there's also inter, like international, between different countries. There are intermolecular forces between them. And these are weak. They tend to be very weak. And when in a solid state, so when you find iodine, for example, if you find it in a solid state, it just means that these intermolecular forces have formed and they are strong enough to hold it in a lattice structure. And iodine, if we actually had a real image of a model of it, it's really interesting how it creates that solid lattice. Lots and lots of mass and geometry involved. And you'll find that simple molecular structures have got a low melting point and boiling point. So a lot of them are liquids, gases at room temperature and pressure, for example, and in comparison to other molecules. So a low, so I'll put low here, low melting and boiling point. So let's have a think, why do they have a low melting and boiling point? What information do you know about them? So pause the video and have a think. As I said before, the intermolecular forces holding these separate molecules together in a lattice, they're very weak. Comparatively, they're relatively weak, or they're very weak. So only small amounts of energy are required to overcome those intermolecular forces. They're easily broken. Therefore, a low temperature is required to overcome and either melt or boil them. So therefore, they have a low melting and boiling points. Now, the simple molecular structures, they do not conduct electricity. So again, pause the video, have a think. Why don't they conduct electricity? There are no mobile charge carriers to carry the charge in a simple molecular structure, so they can't conduct electricity. In terms of solubility, so whether a simple molecular structure dissolves in water or not depends on the type of intermolecular forces between its molecules. It depends on whether the simple molecular structure is polar or not, and we'll study that further along in the course. Let's introduce giant covalent or macromolecular structures. So here we've got silicon oxide. So in this particular example, you can see this will go on and on into the distance. So I've had to cap the structure in terms of its structure, but do understand that this is just going to go on and on and on and on. So these are bonded further and further and further in a huge structure. I've just decided to show you an image this size. A large number of non-metal atoms are joined together by covalent bonds to form a giant lattice, and it's very, very strong. So all of these bonds are covalent. So unlike oxygen, which is going to be O double bond O, that is an entity in and of itself. There's no covalent bonds coming out of that. We've just got one unit and then some intermolecular forces. With this structure here, this oxygen atom is bonded to a silicon atom, which is bonded to an oxygen, which is bonded to another oxygen and another oxygen and another silicon, and it goes on and on and on, and they are all covalent bonds. We don't have intermolecular forces going on here. So that giant covalent structure is going to have high melting points and high boiling points. So pause the video, have a think, why would it have high melting and boiling points? So compared to intermolecular forces, the intramolecular, the covalent bonds that are the only types of bonds that are going to exist in those giant covalent structures, they're really, really strong. So there's a large number of them, and each of them individually are very strong. So a large amount of energy is required to break them apart. Hence, you have to put a lot of energy into the system. So a high temperature is required in order to melt or boil. Hence the high boiling and melting point. So the giant covalent structures also do not conduct electricity. Because again, there's no mobile charge carriers in that particular case in order to carry a charge.